Good morning. So we start our morning session with a talk by John Carlin on counting curves from Calabi Yau. John?
Thank you very much. It's great to be back again here in Miami. I think all my previous visits, I ate at that place called Threefold Cafe near the hotel, but this is my first time hearing talk about Threefolds. So I got the invitation. I was happy to accept, but I didn't really know what I was going to talk about. About a month ago, I figured out what I think I'm going to talk about, but that is to say, all of this is very much in progress. Okay, so there are many ways of counting curves on Calabi Yau Threefolds. There's this great survey paper by Pandharipande Thomas called 6.5 Ways of Counting Curves. That's not all of them. So what do we mean by counting curves? So let's think X to be a Calabi Yau. And well, certainly we can consider the space of smooth embedded curves in X. And well, it's not just a space, it has a derived structure, perfect construction theory, and that gives us a virtual fundamental cycle. The problem is that this space is not connected. So we can't push forward this virtual fundamental point because it's a Varroa cycle. So to count curves, you choose a compactification, and hopefully, not just a compactification chooses the virtual fundamental sets. So the ones that are most familiar to some part of the audience is probably the space of stable maps. So that would be nodal curve and a stable map from C to X, and this gives rise to Gromov Witten invariants. And due to the fact that the space is going to have orbital points in general, these can be graphed. Now, there are many other compactifications you could choose. So far, none of this is special with 3 dimensions or 2 Calabi. Most elements. If X is a complex analytic manifold, then you can consider what you're going to choose. But I'm going to do a precise definition of what you can count here. There are 3 different options, but here choose one X with 1-dimensional support. Polar curves. Okay, and this gives rise to, well, there are 2 sorts of invariants which are defined this way. Donaldson Thomas invariants and Pandharipande Thomas invariant. They're integers. Okay, so despite the fact that these are quite different compactifications, it turns out as expected, they have basically the same enumerative content. So from Witten theory here, and Donaldson Thomas or Pandharipande Thomas theory over here. I should say that it's a hard, difficult theorem, but Donaldson Thomas Pandharipande is known to be equal in the sense of generating content. So I'll just identify them for the okay, so there's a conjecture relating these 2, Homological and Grothendieck, Okounkov, Pandharipande. And this is known for many cases. It's known for local Calabi Yau when with the Bryan, Pandharipande, and Okounkov. Pandharipande is known for spark varieties, and it's known for Calabi Yau, which admits of a nice degeneration. complete intersections of projective space. So there's no invariant case. Now, there's also Gopakumar, which cascades. Except mathematically, no one knows what BPS states. So this is an actual invariant accepted level of physics. But any discussion threefolds will be incomplete at least mentioning this. So the equivalence between these two is subject to the Gopakumar Vafa conjecture. And this conjecture has some meaning even without having known what this side is. Because, as I mentioned, Gromov invariants are rational. These invariants are integral. Gopakumar Vafa invariants are also supposed to be integers, and they're supposed to satisfy some finiteness properties. So if you start with Gromov invariants and produce some numbers over here, like the following the says, a priori you only get graphs and they might not be. So that leads to Gopakumar Vafa integrality and finiteness conjectures, and these are now here. Ionel marker proved the integrality conjecture. Walpuski proved the finiteness conjecture. Okay, so that's sort of the background. Now I try to spend the rest of the talk introducing you that there's actually this one curve property. So some notation. So Z1 X, which is going through the space pseudo-homomorphic one cycle on X. So pseudo-homomorphic one cycle is the sum of some pseudo-homomorphic curves with multiplicity. It's the multiplicity is analytic or non-negative. So this is the three abelian monoid on symbol minus 30. So it's a typical point in the space has a bunch of curves, maybe singular, with some multiplicities. Okay. In fact, it's a topological space. So to apologize with the weak star topology inside the dual space and two poles. In other words, topologist curves. Okay, so what's the neighborhood of something in this topology look like? Well, by some curve, let's say multiplicity 3, nearby point, nearby cycle, and well, this first of all, this curve needs to move, but also it could split into a few different branches. Something like that. That's what happens. Okay, so there's this space, and it's a nice topological space. And there's also a relative version of this space. So if X would be any family of almost complex threefolds, then I can consider that space of relative cycles. So that's just space of cycles. In the fibers, you say the topology is, well, you can topologize inside space of currents and total space, for example. So now I can make the main definition. And this is of a group I'm going to call the Grothendieck group of Calabi Yau one cycles in almost take the direct sum over all almost complex threefolds of just locally constant compact support functions on the space of cycles. I realize I haven't defined this Calabi Yau cycles. So those are just the cycles with pair trivially C1 of the tangent bundle of X. So pairing with C1 tangent bundle of X is a map from space of cycles. To the integers, just continuous, also known as locally constant, and the Calabi Yau cycles is the ones which are correctly. Image of 0. Oh, so this Grothendieck group is a quotient of the space group. It's the quotient by Walpuski. So economics of almost complex threefolds take local constant functions on space of relative cycles. And there are two maps. And like take from here to here, I could evaluate it 0 or I could evaluate difference. And this Grothendieck group is the right, so a typical element in this group, I can write this X almost complex threefold, and F is function from cycles on it to the integers. That's a typical element. This. Now, an enumerative curve enumeration theory if a claim just is homomorphism from this group. To the sum target group G. And this is sort of a silly statement, right? This is a proof construction. All I'm saying is that you have a way of counting curves, you can weight that count by a locally constant function. And if that way of counting curves is invariant under derivation, then better than G. So this group, it has, it's not that the group comes with a lot of additional structure. So it has a multiplication map that sends X and F across Y and G to X is shown Y times G. So I'm representing elements. So for the cycle in X to show union Y is just a cycle of X and the cycle of Y. And it has a unit, which is the empty manifold, because it's exactly one cycle in the empty cycle. The function is just one. It also has a coproduct makes X to there. So there's an addition map from fixed one cycles, fixed one cycles, fixed one cycles. And I can pull back. It's a proper map, so I can pull back. This is for homological. And so what this notation means here is that you pull back at under the addition map and you write it as in the type. So unit, which sends X, you have a 0. You got it at the 0 second. So this means 0C probably at one cycle is almost complex. Threefolds, Y is correct. And oh yes, co-product. Yes, commutative, co-commutative. There's no there's no antipode. Okay, so I need to qualify the statement a little bit. Since we're working with Calabi Yau one cycles, compatibility between multiplication and co-multiplication is a little bit subtle. If we were working with all cycles, it would be tautology, but there's sort of a problem when you might have a cycle which evaluates trivially with C1 with tangent bundle, but splits the sum of two cycles into both their trivial. I think it's still working immediately. Do not trivial integration. So there are also there are more integrations. There's rows of D from the space itself.
Recording in progress.
And what does this do? It's pull back under multiplication by D. Multiplication by D, map from cycles. Cycles pull back here. This is a map of biology. I'm not exactly sure what to call this structure. So it's my kind of surprise here, but the definition of Doan. So homological, you can actually, I believe, calculate this group completely. So I mean, first with the generators are. I'll just keep talking about this. Okay. So let's talk about generators. X, G. So the simplest element we might try to write down in this group would be to say just take a smooth curve and say with multiplicity M. Continuous G multiplicity M. That's a cycle. And if that cycle is isolated, that gives, let's take a characteristic function of that cycle. That would be a nice element. So let's see that. So in is smooth continuous G. And let's try to look at the neighborhood. See copy threefolds. Let's say it's a total space of some of line bubbles, and this is Calabi Yau, when the sum of the degrees is 2g minus 2. So let's just take the degrees to both g and g minus 1. So there's this map from c to the g minus 1 to pick g minus 1 c, sending a g minus 1 to the points to O twisted those points. And the line bonus of degree g minus 1, line bonus of degree g minus 2. Oh, I think someone can read himself. Am I the host or can you read that?
I'm trying to find the vendor. Oh, I guess I got it.
So the line bubbles of degree g minus 1, which have a section that precisely equal to its map, which is dimension g minus 1, dimension g. So the generic line bubble of degree minus 1. So that means the zero section is isolated if you give multiplicity 1. Unfortunately, when you give the zero section higher multiplicity, it's no longer, it might no longer be isolated. So in genus 0, right, so degree k multi-sections of single line bundle, that's the same as sections of L plus L squared plus L of the k over C. So in the case of G equals 0, do this all minus 1 over 1, and these powers will be negative if there are no sections. So the zero section, even with high multiplicity, is this. If you have an elliptic curve, then L and L prime at degree 0. If you choose them generically, then all the powers will be sections. And so there are no sections, zero and isolated. But once you have genus at least 2, then the zero section high multiplicity will no longer be isolated. So we need some more work to define generators. So there's result of Junho-Lee, which plays an important role in the Ionel partners group of Gopakumar Vafa. That there exists small perturbation of the almost complex structure on this L plus L prime, such that there's just no compact to the whole that occurs, except zero section. So if we use this almost complex structure, then the zero section multiplicity and is isolated. J, and the characteristic function of n times zero section. So that is this L X GM. Okay, and the theorem, which in some sense I should credit to Ionel and Parker, because it's really just they're following their argument, is that this group is generated as an algebra on XGM. Okay, so I can say sort of the rough idea of the group. So I begin with an almost complex threefold. Now, if I do generic perturbation to the almost complex structure, then all the holomorphic curves in it will be smoothly embedded, transversely, And sorry, all the simple Homological curves will be smooth, embedded transversely. So you might think that makes space of cycles very nice. And it does make it very nice, but maybe not as nice as you might hope. So a cycle now looks like a bunch of smooth embedded curves with some multiplicities. And the multiplicities give you a little bit of a problem. So nearby this cycle, there could be cycle. Maybe you have something like that, smooth curve. And there could be lots of these smooth curves. The structure of the space of cycles in a form like this is not so nice. So Ionel and Parker called the neighborhood of in a nice cycle a cluster. And so, for example, this thing here, the cluster is sort of trivial sort of cluster because there are no curves in here. So incidentally, there's a conjecture, Bryan and Pandharipande, that in fact this clustering for generic almost complex structures does not happen. The multiple covers are also kind of transversal. And this was recently proven by Chris Lumbo. So you're very, very careful about choosing this kind of structure. And the clusters are also tricky. We don't. Okay, now cluster is the key proposition, the hard step, is to show that all clusters of a given combinatorial type, multiplicity genus, are the same in this group modulo up to sign and modulo clusters of smaller combinatorial. So that's the proof of very sketchy proof of this result. Now, a question, I'll just leave it as a question. This is now from this. Polynomial to Grothendieck here. Inject. I go back and forth sometimes. I think it is injective sometimes. It's maybe less easy to prove. Of course, as a polynomial algebra, it can have many ideals. But this isn't just a map of rings, it's a map of bialgebras. Bialgebras compatible with these operations for OD. And that gives you a lot of constraints of the current OD. So basically, the idea of proving it's injective is you put this ring on some polynomial order and try to use the operations to prove you have there's something in the kernel which is just xg1 plus some terms, and then an element like that you can show has to be non-zero here. Your Gromov with invariants. Yes. Yes, so delta of x g m is some I plus j m x g I answer x g j. So it's like Turing classes in the same program. Okay, so I think that's all I wanted to say about the almost complex case. As I said at the beginning, you want to talk about more enumerative invariants of Calabi Yau threefolds, you need to restrict to integrable complex structures. Okay, so you could just take the definition I gave and restrict to X being a complex group. This is not, as far as I know, a useful thing to do because complex threefolds are too rigid. We have a closed complex and the manifold maybe just has no definitions of the complex structure of the gauge. And it's almost always so you don't have nearly the amount of freedom, the amount of flexibility you need to do this costly decomposition here. And you can't do that. You can't. Okay, so to get the flexibility we need to consider boundaries. So let's consider now one complex folds. So B is some base. I want to just assume this is a family complex analytic threefolds family has proximity. You know, maybe you could assume B is manifold too, but so consider a pair consisting of a family like this, and the second S goes from space of probably one cycles to the tangent bundle of B. And the idea is that just such a pair, I want to associate this space of one cycles in space of curves in whatever sense I want to count them, subject to the condition that S equals 0. So I've increased the dimension by the dimension of B, and I cut it back down by 0 to S. So it's numerically the same properties of just single counting curves and single properties. Okay, so now I'm just going to give the same definition, but using these families. So H naught complex support probably on one cycle is string complex threefolds is going to be direct sum over all of these pair of X to be S of right. And I don't give a compactly supported function on the whole space of cycles. I just give it on the 0 set S. That's a high curve. And the quotient, now I'm quotient by two things. So the first thing with quotient bar is just the same. Now a one parameter family of these pairs. Now we need to quote stop by one more thing because, well, as it stands now, so a given generator here is only going to be equivalent to the generators where the base has the same dimension. So I need the stabilization relation. So that's just going to be the X, the S, and F is the same as X cross bar. Then and the same. That's the stabilization relation. Okay, now the claim is that this generation result still applies. And it's a bit more non-trivial now because we have to show that we're in a context where we have enough flexibility to run the cluster. generated green by GM. So I'll just give an idea of where this flexibility comes from. So suppose we have some complex threefold. Now let's choose embedding I from space of 1 cycles into R. Okay, now maybe where the space is not compact, or maybe it's that type or something that I can't embed it, and it's a little bit too big. I only really care that this map be embedding over the support of the function in question. So it doesn't. Let's just assume it's in. Okay, so then I want to consider x cross n over. And now I need a function s. The s is supposed to go from the space of relative cycles. Now, what's the space of the relative space of cycles in this? Well, the cycle here is just pointed at Rn and the cycle. This is z1, zy, x cross. And I should go to the tangent space of Rn, which is just R. Okay, I'm going to send z and x to x minus t times I of c. Okay, so this is a one parameter family. T 0. So at t equals 0, this term is in here, and it's just a stabilization of my original thing, which is equal to t equals 0. It's the stabilization of x. And at t equals 1, what happens? So let me just draw a picture. Yeah, so here I'm going to draw the z1, cy, x cross around, mapping down to R. Okay, so at t equals 1, sorry, t equals 0, the 0 set is just the 5 versus. So this is S0 inverses. And what happens when I go to S1 versus 0? Well, it becomes a graph. It becomes a graph of this function I. It's S1 inverse of 0. It's the graph of this function I. And I is an embedding. So S inverse of 0. Projecting down to this base B, prime is embedding. So that means now in the family I have at a given fiber, there's only one cycle that I care. And if there's only one cycle that I care about, well, I can just throw away the rest. Basically, just a small neighbor of this in the universal family over space of cycles x inverse 0. And now it's a highly non-proper family, but that doesn't matter. The point now is that I said at the very beginning, right, you can't deform complex threefolds very well. But if your complex threefold is a small regular neighborhood of a one cycle, then there's plenty of different. So once you do this transformation, you're in a situation where you have plenty of information, you can start your own same cluster argument as before. Okay, so now, now that we have this group, we'd like to consider some actual enumerator invariants. So we have Gromov generated function going from this group to now the formal parameter t parameter t, that's the Gromov partition function, and it's also say the Pandharipande Thomas partition function, which you count stable pairs supported under group one cycle, and that is going to give you now series in Q. Maybe a little trees. Okay, this is a sort of technical remark. For the Donaldson Thomas partition function, actually not the non-Thomas group, because the sheaves you count in Donaldson Thomas theory, the support of one of those sheaves is a one cycle union some points, unions in a zero cycle. So that's not actually the group under this group, but just categorized one cycles. It's not a big issue. One, because Donaldson Thomas theory under the equivalent. This theory just counts things support in the zero cycle locally. In fact, that was sort of the motivation for the notion of stable pair. Anyway, that these zero cycles don't float away, so the theory is more computed. Okay, so the MNOP conjecture states that these are the same up to a change of variables, which I remember. So this is supposed to equal 19. Of course, makes sense of this. Can't evaluate t, the formal variable. You can't evaluate this a priori at this point. So there's part one of the conjecture is that this partition function is in fact a Grothendieck function. Let me just say this. So of course, to prove this now, it suffices to check generators X, GM, and this is essentially known under Thomas, Bryan under they calculated Gromov invariance of local curve, and Okounkov and Pandharipande calculated the Donaldson Thomas invariance. Okay. How much time do I have? Check.
9:43.
9:43. Okay, great. Yeah, so I should say much more about this because there's quite a bit of disconnect between what exactly they calculated and the setup I have here. So you'll recall that this local theory of local curve, the cycles, the zero cycle, zero section with some multiplicity. This is not an isolated point. So, what do I mean by this generator XGM? So the almost complex case, there was a deformation of the almost complex structure. We did a deformation of an almost complex structure the space, which makes this nested. That gives you definition to generate this group. Now, that's an almost complex structure. That's not a valid definition of an element in this group. So to get an element in this group, you need to sort of first you run this argument, and then you try to do some perturbation away from the zero section. But now, why should such a perturbation work? So this family is actually S1 equivariant. So I can see it extra efficiency. S1 happens here, and hence S1 happens on space of cycles. And the fixed locus it's just a zero section. If you know if your cycle is not the zero section, then okay. So anytime you have an S1 equivariant cycle, or reversal fundamental cycle on just any space X with an S1 action lifts canonically the cycle on the fixed. This is the S1 localization. So now I can say what these calculators actually mean. So what they mean is that you look at the moduli space for this total space, it's not compact. However, the virtual fundamental cycle lifts to the fixed locus, and the fixed locus is this one. So given that, you can actually compute. And you have a one-line answer, and you can compute. Very difficult computation, but they do. Now, we need a little bit of formalism, though, to relate that notion of computation to this group. I just want to write down. So, should be different. So I'm going to make an S1 equivariant version. So let's start this ordinary group here. So I have a map from this group. Maybe I have to practice in blue actually. So we know this. The only difference is that with S1 here. Okay, so that means that I use S1 equivariant factors as the component. The base hasn't as an S1. And that's what this fixes. Everything is equivariant. The second axis equivariant. Because otherwise the definition stays the same. So I can definition. And this map forgets the S1. Another. And there's another group. Like this, where I look at functions. I still may have everything equivariant, but now I also use functions which are only defined on the whole space of cycles, but just on the fixed point. the cycle strip fixed by S1. Now, an enumerative theory of curves, which satisfies S1 localization, gives you how to map out of all these groups. In fact, this map ascends to a map here is exactly the statement that the virtual fundamental site that you're integrating against is equivalent to canonical lists. And now, now we can do some sort of background chase to try to show that ZGW equals ZP. So how does it work? So these elementary generated, they most naturally live here. That's what our order. And we have two maps out of this group, which we're trying to prove agree. Now we know this group here is generated by elementary clusters. So in order to prove two things agree, they can both agree on one. So to prove they agree, I just have to prove they agree on elementary clusters. So it would suffice to show that they agree on some subset of this group, on which surjects on the element. So if we find it, so elements here, whose image on which two invariants agree, and whose images invariant. And any lift of XGM will do. So I can have a lift XGM to this group. That's all I have to drag. XGM is the image of something here. And to do that, well, the content is to do some S1 equivariant perturbation to get rid of all the cycles which are going on. Which I believe you have the flexibility to do. There's one. Question?